Okay, good afternoon, everyone. Let's get started with lecture 2 of EfficientML.ai. So today we are going to learn about basics of neural networks. As we have seen in the last lecture, there's a big gap between the supply and demand of AI computing, where the demand of computation is growing really fast, as indicated by the model size of recent large language models. And Moore's law is roughly doubling every 2 years, but the deep learning models is getting more than 4 times larger every 2 years. So there's going to be a gap, which motivated us to bridge this gap with model compression and acceleration techniques. So in the last lecture, just do a quick recap. We went through several examples from vision to language to visual language model, and also the multimodality models to give an overview about the latest advancement of AI computing and how much demand of computing they need to motivate us to build these efficient algorithms and systems to accelerate efficient AI computing. So today we are going to start with those details, technical details, to first review the terminology of neural networks, such as neurons, synapses, activation, feature, weight, parameter, etc. And also we are going to review the popular building blocks with the fully connected layer, convolution layer, group convolution, depthwise convolution, especially to understand the computation demand behind that, including both the memory demand and also the computation demand. We're also going to introduce those efficiency metrics, including the number of parameters, how to calculate the number of parameters, the model size, the peak activation size, the MAC, flops, OP, ops, what is the difference between them, what is the relationship between them, latency, throughput. And if you have time, we're going to go through Lab 0, which is a tutorial on PyTorch. So Lab 0 is optional, but make sure we also wanted to make a submission on Canvas. It's not going to be graded, but it'll get yourself familiarized with the procedure. How do we submit homework on Canvas? And for all the announcements related, please keep an eye on our course website. We are going to make all the announcements, the lecture slides, lecture videos, homeworks, assignments, everything will be released at our course website, which is EfficientML.ai. So if you have not bookmarked it yet, make sure to bookmark our course website, EfficientML.ai, and check it every week to get the latest slides, videos, and homeworks. We have 5 labs. The schedule of the lab release will be also announced in the EfficientML.ai website. So make sure you bookmark our website. Okay, so let's jump into Neuron and Synapse. So as shown on the right-hand side, we have a synapse on the left, and we have input axon on the left, output axon on the right, and we have the synapse that compute the weighted average of the input axon. So the synapse is basically the weight of the neural network. So the right part is the synapses, right? So we use the terminology interchangeably between synapses, weights, and parameters. So if you heard these terms, they mean the same thing. And the neurons, features, and activations, we use these terminologies interchangeably. They also mean the same thing. So in this example, we have a 2-layer neural network and get an output. So the dimensionality of these hidden layers determines the width of the model, right? So the width of the model matters a lot to the efficiency of neural networks. So you can design a wide but shallow network with the same number of parameters as narrow but deep neural network. So any guess which one is more accurate and which one is more hardware efficient in these 2 scenarios? One is a very deep but narrow neural network. The other is a shallow but wide neural network. Which one is more hardware friendly? Wide and shallow. And why is that the case? Exactly, fewer number of kernel cores, and I have more parallelism to fully exhaust the number of threads in the GPUs. So from the efficiency perspective, a wide and shallow network might be more efficient. In the meantime, from the accuracy perspective, usually a deep network helps a lot. So there is a trade-off. You don't get a free lunch on both sides. So that's the beauty of neural network architecture design, where we're going to visit in the later part of this lecture. How do you trade off between this hardware efficiency and also the accuracy? So let's visit a few popular neural network layers, starting from the fully connected layer, also called a linear layer. So in a linear layer, you have a weight matrix, which is of dimension Ci, input channel, times Co, which is the output channel. Okay, so the number of parameters here is Ci times Co. Okay, and this is the input activation Ci, and this is the output activation Co. So that's the input feature dimension. Usually, when we are talking about efficient AI computing, it's super important to understand the dimension of each tensor. Okay. Later, when we are going to build the model to calculate the flops number of operations and also the model the parameter size, the model size, it all concerns about the dimension of each tensor. So it's very crucial to figure out the dimension of the input feature, output feature map, weight feature, and also the bias. Especially the bias, when we are going to learn about the efficient on-device training, we are having a technique called bias-only update, or recently the LoRa, which concerns about the bias. So we're going to revisit that in later part of the lecture. So very simple, output equal to the weighted sum of the input. So that's the fully connected layer, also called a linear layer. What do we if we have multiple inputs? So here we have a batch size of 2. We have 2 inputs, right? So the weight dimension stays the same. It's Ci times Co, but the input becomes n times Ci, and the output feature map becomes n times Co. Convolution layer. So the output neuron is no longer connected to all the inputs, but is connected only to the inputs within the receptive field. Okay, so we have a input feature, and this is the spatial dimension. Now we just assume it's 1D convolution, and later let's jump into 2D. In this 1D convolution, this is the channel dimension, this is the spatial 1D spatial dimension, and we apply this green filter. Here we also have the input channel dimension Ci, and here we have the Kw, which is the filter dimension, and then we have multiple such filters. Okay, each filter is going to convolve with the input and produce one output, and we can shift this sliding window by 1 to get another output. And we can shift it again to get another output. So as a result, the output feature channel dimension is 3, since we have 3 kernels for the weight. And the weight dimension is basically Ci times K times Co. Since each kernel dimension, we have Ci times K, and we have Co, this amount of kernels. And finally, we have a bias with the dimension of Co. And now let's generalize that to two-dimensional convolution, 2D conv. Okay, as we can see, we added another dimension. It's 2D convolution, but looks like the feature map is 3-dimensional. That's because for each XY location, we have a channel dimension. Okay, the channel dimension. So for 2D convolution, the feature map is actually 3D. So the activation map, the H times W, assuming, imagining you have a picture, width is W, height is H, and then we'll apply a filter, which is KH by KW, which is the filter dimension for the H and W dimension, with the same input channel dimension Ci. And then we have multiple such filters, 3 such filters, which is equal to Co in this case. And we can shift it by 1 to get another output, shifted by 2 to get the another output. And we can shift in another dimension on and so on to get the output feature map, 3 by 3 output feature map. And how do we calculate the size of the output feature map? Is equal to the size of the input minus the size of the kernel plus 1. And why plus 1? Because you can shift kh minus 1 this amount of shifts, and applying each shift you get a one more output. So ho equal to hi minus kh plus 1. In this case, the hi equal to 4. The input is 4 by 4, and then the kernel size is 3. Therefore, the output dimension is 4 minus 3 plus 1. It'll be 2 in this case. Let's also talk about padding. Okay, so padding can be used to keep the output feature map the same as the input feature map. Otherwise, using convolution, the feature map will get smaller and smaller as you have a deeper number of layers. So one common way is to do to apply zero padding, to pad the input boundaries with the 0, which is the default in PyTorch. There's, for example, in this case, the original height and width equal to 5 in this animation. The kernel size is 3, so the output height and weight equal to 5 plus 2 times 1, 2p. Okay, padding equal to 1. We pad 1 on each side, and minus 3 plus 1 equal to 5. So the output feature map is the same as the input. Compared with the initial version, like in here, the output becomes smaller. The input is 4 by 4, but the output becomes 2, as we can see on the example here, right? Initially, the input was 4 by 4, the output becomes 2. And after we apply padding, the input and output are both 5 by 5 in this case. So we can have zero padding. There are also other methods to apply padding. For example, using reflection padding. Okay, so for example, right here, the padded number is the reflected value of the original feature map. We can also apply the replication padding to use the closest number and replicate that to apply the padding. But the zero padding is still the widely used approach. So after padding, let's now talk about the receptive field. For example, the output pixel here, how many pixels can it see in the previous layer? It can see 3 by 3 pixels if the kernel size is 3 by 3, right? And each pixel here sees another 3 by 3. So how many pixels from here to here? Actually 5 by 5, right? And one more layer, you get a 7 by 7 receptive field. Why do we need a large receptive field? We want to understand the relationship between different pixels. For example, a car on the road versus some pedestrian also on the road, the relationship between the car and pedestrian means whether you can drive or you should avoid the pedestrian, right? So the relationship matters for those high-level vision tasks. And why people invented transformers later? Because transformer give you a global receptive field. You can see every pixel can attend to every pixel in vision transformers we're going to cover later. So the principle is that a larger receptive field helps a lot. It's very crucial to high-level image understanding. So with 2 layers, 3 kernels, we can see a receptive field of 5 by 5. And in general, the equation is here. With L layers, the receptive field size equal to L times kernel size minus 1 plus 1. So for 2 layers, kernel size equal to 3, the receptive field is 5. And if you have 3 layers, kernel size is 3, the receptive field is 7. So the problem is that for large images, in order to have a large receptive field, we have to have very deep layers. We need many, many layers. And we just talk about that in the early part of the lecture. If you have too many layers, you have lots of kernel calls. You also have to store a lot of activations. Activations has to be stored during backpropagation, increasing our training memory. So how do we have a large receptive field at the same time? We don't want to have so many layers. So we can downsample inside the neural network. One example is to use the strided convolution layer. Okay. So compared with stride equal to 1, which is on the bottom, so on the top shows the stride equal to 2. Okay. So rather than every pixel sees the adjacent 3 by 3 pixels, now you see 5 by 5. Okay. The adjacent green adjacent green 3 by 3 rectangle is shifted by not 1 pixel but 2 pixels. Okay, you can see this 3 by 3 versus this 3 by 3 is actually shifted by 2. So that's a stride of 2. Every time you don't move 1 step, but you move two steps. So that's the strided convolution. In this case, for 2 layers and kernel size equal to 3, the receptive field becomes 7. Okay? Previously it was 5, now it was 7. We have a larger receptive field with the same number of layers. So this is very helpful for reducing the number of layers, reducing the number of weights, reducing the number of activations, but have the same receptive field. But of course, you may lose a bit accuracy because the model capacity might be smaller. But everything is trade-off. There's no free lunch in deep neural network design. Everything is about constrained optimization, which makes the optimization highly interesting. Okay, so our goal is to continue reducing the number of parameters. Okay, so for convolution layer, each output channel is connected to all the input channel, Okay, how to reduce the amount of computation? People invented this group convolution layer. Okay, so previously we have just one group. Every output channel is connected to all the input channel. Now we can divide them into 2 groups. So for the first group, only half of the input channel is connected. And for the second half, that's the second group. The feature map doesn't change, stays the same as before. But the number of weights will be g times smaller. Okay, will be g times smaller. So CO will be divided by g, and CI will also be divided by g. And we have g amount of such filters. Okay, therefore the total amount of weights is reduced by g. Okay, so that's the group convolution layer. And what is the extreme of group convolution? The number of group will be equal to the number of input or output channel. Okay, so which is exactly this case. Previously we have 2 groups. Now we have CO groups. In this case, it's 8. Right? We have 8 groups. So each output channel is only connected to 1 input channel. Okay, so the number of input feature and output feature stays the same, and the number of weights will be C, which is the same for CI and CO. So we just use C times KH and KW, which is the extreme case of group convolution, called a depthwise convolution layer, which is quite widely used since 2015, 2016, when MobileNet was invented. Next, pooling layer. We want to have a smaller feature map. Originally, the input image might be like 1K by 1K is pretty large, and we want to have a smaller feature map and condense the information, right? This is actually quite useful for large resolution input. We want to quickly pool the feature map to make it smaller. So here we have an example with the 4x4 input feature map. And how do we pool it to 2x2? We can either use max pooling. So for every 4x4 input, we find the max element within that group. Or we can do this kind of average pooling, finding the average in the blue area, finding the average for the yellow area to do the average pooling. The good thing about pooling is that there's no learnable parameters, okay? Or you can assume, yeah, so that contains zero weight, which is very parameter efficient. Next, let's talk about normalization layer. So batch normalization came roughly in 2015 or 6, New Rips 15 or 16, roughly 7-8 years ago, which later becomes quite useful to stabilize the training. For example, the layer norm also becomes super helpful in the age of attention transformers. So what exactly is normalization? So we will normalize the feature map to make the optimization faster. Okay, so how do we apply that? So we minus the feature map minus the mean of that tensor, okay, and divided by the sigma. Okay, so we want to make sure we want to minus the mean and divide it by the standard deviation over a set of pixels or tensors if it is null vision. Okay, so this is a reminder how to calculate the mean and the standard deviation. And note here we have a small sigma right here. Okay, so that is due to we want to avoid dividing by 0. So we put a very small number over there. And then we learn a per channel linear transformation, okay, which is indicated by the scaling factor and also the bias right here to compensate for the possible loss of representational ability. Okay, so how do we define this set of pixels or set of tensors? On the bottom, it shows 4 different ways to find that group of pixels. The first one, very widely used in CNNs, called batch normalization. Okay, so it's normalizing across the n dimension. N is the image dimension. Okay, and also we just use a single C dimension across all the H and W height and width dimension. Okay, normalize across different batches. Second one is quite widely used in the attention mechanism. So for different input, for each input, okay, across different H and W and C, C is the channel dimension, make sure it's normalized. So for each token in the attention mechanism, when you are doing the attention, after each token is normalized, then the attention map makes sense. Otherwise, if it's not normalized, the attention map will be much harder to optimize. There's also the instance normalization. Okay, just normalize across the H and W dimension, not the C dimension. And when the C is too large, there's also the group normalization on the right, which divide the C by several groups and only normalize within that group. There's a lot of tricks we can play for the normalization layer. For example, when we are doing fine-tuning, actually normalization layer, the number of parameters is very small, so we can only fine-tune the weight, the bias, and also the scaling factor in the normalization layer, making the fine-tuning much more computation parameter efficient. The normalization layer can also absorb the transformation of such as smooth quantization. So without incurring another kernel call, we can absorb lots of the computation in the IP log or fuse it with the normalization layer. So we are going to visit them in later part of this lecture. Okay, next one is the activation function. So we have seen many different activation functions, but let me talk about the efficiency and accuracy trade-off here. Sigmoid, very ancient activation function. It ranges between 0 and 1. It's very easy to quantize, very efficient to quantize because the dynamic range is very limited and it's fixed between 0 and 1. But what is the drawback? Gradient vanishing, right? So if the value is super small or super large, there's no gradient. And then people come up with ReLU, okay? When it's positive, the gradient never vanishes. But when it's negative, the neuron is basically dead. There's no way to put it back because there's no gradient anywhere when the value is smaller than 0. But what is good about it is that it's very easy to sparsify. Since we're going to talk about pruning and sparsity in the later part of this lecture, the ReLU activation function naturally brings sparsity because a lot of the activation, once they are negative, they become 0, and 0 multiplied by anything is 0. So you don't have to compute on it. You don't even to store it. You can just store a mask showing that this is 0, just using 1 bit. And the gradient is 1 everywhere else. Okay, so you don't even need to save this feature map. You can just save a bit mask for that tensor. If it is the bit mask is 0, then the output is 0. If the bit mask is 1, it will just copy the feature map from the previous output. So very activation friendly, sparsity friendly, simple. But what is the downside? The dynamic range is super large. It's not easy to quantize. So people invented ReLU 6, okay, ReLU 6 to cap the largest value to be 6. That's why people call it ReLU 6. Okay, it's purely empirical, and that makes the quantization range much more constrained. Reducing the dynamic range makes it easier to quantize. Another drawback is that there's no gradient in the negative region. So people invented leaky ReLU. Okay, there's a smaller slope on the negative side. Okay, so you can also have the gradient flow in the negative region. But the downside is that you no longer have this sparsity benefit. If the value is small, it's negative. It's no longer 0. And then people are using neural architecture search find a very interesting activation function called a switch. Okay, switch basically very similar to ReLU, but it's using x divided by 1 plus e to the minus of x. But people later find it hard to implement in hardware, right? So people come up with an approximated switch called hard switch. Okay, so when x is smaller than minus 3 is 0. Above 3 is just x, and in between that, the value is x plus 3 divided by 6. Okay, so all these activation function somehow have something to do with efficiency, like sparsity, quantization, dynamic range, easy to implement. So that's the story behind the progression of different activation functions. And finally, transformers. Transformers are getting super important since the invention in 2017, 2018. We'll learn more about transformer architecture in lecture 12. We have a dedicated lecture just to talk about transformers, the entire pipeline, entire structure of transformers. So let's just give a very simple overview today. So there are 2 stages, the encoding stage and the decoding stage. For each stage, we have a multi-head attention followed by FFN, feed-forward network. And this is the architecture for the attention mechanism. You have 3 tensors, Q, K, V, query, key, and the value. We do a attention scaled dot product attention, and then pass it through a linear layer to get the O, Q, K, V, O. Those are the 4 activation tensors. And there's no weight in the attention mechanism. That's in the middle part. Only weight in the QKVO transformation. Okay? And the detailed way to do that for the query key value, the design is actually very analogous to the retrieval system. Just take a YouTube search as an example. The query is like the text prompt in the search bar. Okay? And the key would be like the title or description, some short information about the video, and value would be the corresponding video. So you do a dot product with the query and the key to get the similarity, and use the similarity to fetch, to do a weighted average of the value. And remember, we want to divide the Q and K by a normalization factor, which is square root of D, to accommodate for the dimension change to make the optimization more stable, and followed by the softmax to get a attention map, an n by n attention map, and use that attention map to do a weighted average, weighted sum of the value. Okay, and later part of the lecture we are going to visit in the attention map. The n by n attention map could be the bottleneck for both computation and the on the memory, since this is growing quadratically with the number of token n. Okay, and for images, the number of token also grow quadratically with the resolution. So n squared would be super expensive. So there's sparsity opportunity. Not all token need to attend to each other. Sparse attention, we're going to introduce that. And also flash attention, we can use in place attention to minimize the data movement so that we can have a constant, almost constant memory, but the flops is not reduced. So in order to deal with that problem, we are going to introduce long context techniques, all related to this attention mechanism. So although attention itself doesn't have any weights, there's a lot of interesting stuff we can explore. Even the KV cache, they become the activation when we are calculating the KV cache, but when we are using that to generate the next token, they become the weight to when new tokens is generated. So how do we quantize, how do we prune the KV cache? We're also going to cover that in later part of the lecture. Let's continue the lecture to talk about the efficiency metrics. How should we measure the efficiency of neural networks? So there are several pillars we want to achieve at the same time, but it's pretty hard. Having a smaller model. So when you're uploading the model to the Apple Store, it's pretty small, right? You don't want to download a model that is hundreds of gigabytes. That is too hard to download. And also, we want to have a faster model. Okay, give you the real-time prediction, never miss a pedestrian on the road for a self-driving car, and also generate images instantly on your phone, for example. And also greener model, taking less battery. For example, on the iPhone, on the mobile devices, you don't want to drain your battery with its AI applications. And that concerns the storage, the latency, and the energy, right? And computation, the memory is determining the storage, latency, and energy. So we are going to introduce several efficiency metrics on the right-hand side. Some of them are memory related, some of them are computation related. On the memory side, we'll introduce how to count the number of parameters, the model size, the total activation size, and peak activation size. For the computation related, we're going to talk about what is a MAC, what is flop, what is flops, what is op, what is ops. So let's first talk about latency. So what is latency? Latency measures the delay for a specific task. And let me directly show you an example. So on the left-hand side, it's high latency, right? To predict the segmentation mask of output takes a long time. And right-hand side is lower latency, only 46 milliseconds to process each frame. What is throughput? It measures the rate at which data is processed. On the left-hand side is low throughput. You can process 6 videos per second. On the right-hand side is high throughput, 77 videos per second. This is from the temporal shift module paper for video understanding we are going to introduce later. So what is the relationship between latency and the throughput? Does higher throughput translate to lower latency? Does lower latency translate to higher throughput? So let's see an example. The first design, the latency is 50 milliseconds. So every 50 milliseconds, we can process one image. So how many images can we process every second? It's 20, right? On the design tool, we have higher parallelism. We can process 4 images at the same time, each taking 100 milliseconds. So latency to process each image from start to end is 100 milliseconds. And the throughput would be 40 images per second, since we are processing 4 such images at the same time. So on the left-hand side is having a lower latency but lower throughput. Right-hand side is having a higher latency, but higher throughput. As a result, higher throughput doesn't translate to lower latency. And lower latency also doesn't translate to higher throughput. On the mobile, we mostly care about the latency. On the data center, on batch processing tasks, we care about the throughput. So those are very important metrics, latency and throughput. Sometimes we want to make sure we report both. So what is the factors that impact the latency? So there are two factors that is determining the latency. One is the computation, one is the memory. Okay? The T of computation equal to the number of operations in a neural network model divided by the number of operations that the process can process per second. And the bottom is the hardware specific characteristic, and the top is neural network specific. And the T memory also is determined by two factors, the activations and also the weight, to move the activation and move the weight. So this is about inference. If it is training, it also concerns about communication, about the gradient. So T data movement of weight equal to the weight, the model size, divided by the memory bandwidth, hardware specific, neural network specific. And T data movement of activations is determined by the input activation size plus the output activation size. This is first order, all these are first order approximations to give you a ballpark estimation divided by the memory bandwidth of the processor. So which one is more expensive? So this is a figure showing the energy consumption of different operations from a 32-bit integer add to accessing a register file to multiplication to accessing the SRAM cache to accessing the DRAM cache. And we can to access the DRAM memory. We can see that accessing the DRAM memory could be super expensive. Okay, 640 picojoules versus just doing a 32-bit add. It's just 0.1 picojoule. So accessing the memory is a lot more expensive than doing the arithmetic. Magnitude more energy is consumed by accessing the memory. So keep in mind, computation is cheap. Memory data movement is expensive. So it is the data movement that is truly the battery. Data movement is expensive. So there is the number of weight via a neural network. So the number of each kernel has caged times C in. We have C among together. We have terms together and the total number of parameters of a here. For a we have a amount of such altogether G times smaller compared with convolution with the same dimension. But G equal to CO times K times K company. The parameters for popular neural networks for AlexNet. Right? So let me do the calculation first here, where the channel number is input channel is 3, output channel is 96, and the kernel size is either 11 by 11. Or parameter is 11 by 11. Okay? And similarly, we can calculate the layer divide parameters by 2, since group size is 2. So I'll give you 1 minute to calculate, to think about the layer number of parameters for the next layer. Okay? Here, 13 by 13 image size and 3 by 3 convolution. the channel number is 384. So here's a quick answer. Since the input channel is 256, output is 384, and the channel number is kernel size is 3 by 3, this is the way to calculate that. And finally, for the fully connected layer, you just multiply the input channel with the output channel to calculate the total number of weights, which is 61 million in total. So how does that translate to the model size between the number of parameters to model size? What's the relationship? You want to multiply the number of bytes for each parameter with the number of parameters. Okay, so the number of parameters with multiplied with the bit width, you get a model size. So for example, AlexNet has 61 million parameters. If each weight is represented by the single precision 32-bit number, and how many bytes are there in a 32-bit? 4 bytes, right? 32 bits equal to 4 bytes. So 61 million times 4, you have 224 megabytes. So make sure you have the prerequisite so that you can understand these concepts relatively easily, how many bits per byte. And if you want to quantize the weight to integer, right, to 8-bit integer, what is the total storage for the weight? So 8-bit, that equal to 1 byte. 61 million parameters, that's 61 megabyte. 61 megabyte, 4 times smaller, right, compared with 32-bit. And later part of this lecture, we are going to learn about activation aware weight only quantization, AWQ, to quantize it to 4-bit. Okay? 4-bit will be another 2 times smaller, so that you can fit large language model locally on your laptop. Okay, so now let's switch gear to talk about the total and the peak number of activations. So activation is the bottleneck for seeing inference, not the parameters. For example, here from ResNet to MobileNet, number of parameters is reduced a lot by 4 times, more than 4 times. But the activation, the peak activation didn't decrease, but increased. So for how to reduce the activation, activation is very crucial. The deeper the layer, the more number of activations, usually that's the case. And also, the peak activation determines the memory bottleneck. For example, the third layer here determines what is the max memory you are going to consume when you are doing the inference. So the imbalanced memory distribution happens, very popular for CNNs. Why is that the case? Because the first couple of layers you have very high resolution and it's square, and later you have a lower resolution due to downsample. For example, if a microcontroller has only 256 kilobytes of SRAM in the of SRAM to hold these activations, you want to make sure the largest layer, for example, here, doesn't exceed the SRAM so that you can put all the activations in the fast SRAM. Activation is also becoming the memory bottleneck in training. In CNNs, for large language models, the number of parameters is also the bottleneck. That's why people later proposed this model parallelism to do the sharding of the weight. So here is an example for the CNNs where this is showing the number of parameters versus the number of activations. The number of activation is like 7 times larger than the number of parameters when you are doing training. Due to the batch, the activation is pretty large, occupying a lot of the GPU memories. And here from Ryzen 50 to MobileNet V2 1.6, they pretty much have the same accuracy. So it's apples to apples comparison. The parameter is reduced by 4 times, but the main memory bottleneck, which is the activation, didn't improve much, only 1.1 times, only 10%. So optimizing the activation is hard. And usually for CNNs, the distribution for the weight and activation is different. The yellow part is the activation. The blue part is the weight. It's U-shaped. Okay? Initially, the activation memory is large. Later, the weight memory is large. This is due to it has high resolution. and this is due to it has larger amount of channels. So this is calculating the number of activations of AlexNet. So C times H times W, that's the way to calculate the activation size. And if you add them together, you can see this is the total amount of activations for AlexNet. And the peak activation is roughly first order approximation, number of input activation plus the number of output activation. Okay, now let's switch gear to talk about compute bounded metrics. For example, MAC. So what is a MAC? It's not McDonald. It's multiply and accumulate. Right? Multiply and accumulate. So A equal to A plus B times C. That's one MAC, one accumulation and one multiplication. It usually comes as a single instruction in GPUs. So for matrix vector multiplication, how to calculate the number of MACs? For example, on the top right corner, this is a matrix vector multiplication. Okay, so we are going to produce M, okay, M outputs. In order to produce each output, we need to compute N multiplication as. Okay, in order to produce each output, we need to calculate N max. So altogether, we have M times N max. What about a matrix multiplication, short for GEMM, general matrix multiplication? On the right-hand side, we have a M by K matrix times a K by N matrix, and produce a M by N output. So we have M by N output. In order to calculate each output, we need K max. So altogether, we need M times N times K max. So here we're showing the number of max for different layers. For linear layer, we just talk about that. The max equal to the C in times C out, assume batch size of 1. And for convolution, it's actually multiplying 6 terms together. Okay, so we are calculating, this is the amount of output features we have to calculate, which is WO times W output, H output times CO. Okay, and in order to compute each output pixel, how many max do we need? We need the entire kernel to be convolved. So that's KW times KH times CI. So multiplying them together, we have to multiply these 6 terms together. 3 from here and 3 from here. Okay, that's the way to calculate the convolution max. With group convolution, okay, we just divided by G. G is the number of groups. And for depthwise convolution, CI equal to G, so we canceled one term, multiplying these 5 terms together. CI gets canceled due to G equal to CI. And this is calculating the max for AlexNet, for example. Each layer multiplying these 6 terms together. If it is group convolution, divided by the number of groups, in this case, 2 in this case. And finally, for the last 3 fully connected layers, it's just input channel times the output channel, 2 terms multiplied together, where ultimately you have 724 million max in total. Okay, so now let's switch gear to talk about flop and flops. So one multiply is a floating point operation. One add is also a floating point operation. So flop is short for number of floating point operations. So how many flops are there in a MAC? A MAC has a multiply. A multiply is a flop. A MAC also has an add. An add is also a flop. So one multiply and accumulate operation is equal to 2 floating point operations if the operands are floating point numbers. For example, AlexNet has 724 million max. The total number of floating point operations will be 724 times 2. That's 1.4 gigaflops. Okay. And what is flops? So that's short for floating point operations per second. The number of flops divided by how many seconds. So that's a performance metric showing how fast are you processing these floating point numbers. So what is an op? We don't always represent the numbers in floating point. Sometimes we represent them in integer, right? So both floating point operation and integer operation, all kinds of operation, even bit mask or even XNOR operation, we can call it the op. Okay? To generalize, the number of operations is used to measure the amount of computation. For example, if AlexNet has 724 million max, if each number is represented by, say, binary or ternary or floating point or integer, whatever you have, any operation can be counted as an op. So 724 million max will be equal to 1.4 gigaops. And similarly, operations per second, OPS, equal to the odd number of operations divided by the number of seconds to complete this operation, which is a performance speed matrix. Hey, before jumping into the Lab 0 tutorial, let's give a short summary of today's lecture. Reviewed the basics of neural networks, output activation, synapses, weight, popular layers, including FC layer, convolution layer, depthwise convolution, pooling, and normalization. We also introduced efficiency metrics, parameters, model size, activations, max, flop, flops, op, and ops.